In Lesson 41, Paul explained his solution to the Lesson 40 homework. He then reviewed the trigonometry required to report the inclination of the MPU 6050 IMU. Our Lesson 41 homework was to measure and report the tilt of the IMU. In Lesson 42, Paul explained his solution to the tilt assignment, and our assignment in Lesson 42 was to expand the tilt concept, measuring and reporting the pitch and roll of the IMU, complete with an indication of direction. In other words, pitch up, down, roll left, roll right. This homework addresses both Lesson 41 and 42. This assignment has taken me an outlandish amount of time to complete. I couldn't get my head around the idea that the pitch equation ignored roll and the roll equation ignored pitch. I understand that Paul likes to strip things down to the basics, but I couldn't let go of this one. Even worse, I found the same, much more complicated pair of equations on numerous YouTube channels and manufacturers' websites. Over and over, I found the same pair of equations, but different from the equations Paul was leading us towards, and no derivations to be found. So I set about to see if I could derive those equations myself and determine the pros and cons of each form of the equation. Paul's correct, as usual. Sketches really help to focus your thoughts. There's quite a few sketches and a bit of trig in what follows. If you have the patience, I'd really appreciate your feedback or comments about my logic, my trig, or whatever. But if you'd rather avoid all the theory, the chapter markers should help you skip ahead to the code review and the practical tests. As we did in the Lesson 40 homework, we start by assuming that the IMU is flat and stationary on a horizontal surface. We know that the only force applied to a stationary IMU is the force of gravity. We also know that when the IMU is flat in the x and y axes, the force of gravity will strike the z-axis sensor at 90 degrees, as shown on the left. The IMU will report the full force of gravity as zxl. Now imagine we tilt the sensor upward by theta degrees, as shown in the diagram on the left. As you can see, only a portion of the force of gravity strikes the z-axis at 90 degrees now. The remainder strikes the y-axis at 90 degrees. If we're going to calculate the value of these forces, we need to know the value of the angle shown on the left with the question mark. You may recall that the sum of the angles inside a triangle is 180 degrees. Consider the triangle highlighted in green. This triangle contains our pitch angle theta. The left side of the triangle is the force of gravity, which we know hits the horizon at 90 degrees. We'll call the remaining angle alpha. We can say that theta plus 90 degrees plus alpha equals 180 degrees, or alpha equals 90 degrees minus theta. We'll call that equation 1. Zxl is the component of the force of gravity that hits the z-axis sensor at 90 degrees. So looking along the back side of the IMU, we can say that 90 degrees plus our unknown angle plus alpha equals 180 degrees, or the unknown angle is 90 minus alpha. Let's say that's equation 2. Substituting equation 1 into equation 2, we get that the unknown angle is 90 degrees minus 90 degrees plus theta, so that proves the unknown angle is theta. Let's see if knowing theta and zxl is enough to determine tilt or pitch for an otherwise flat stationary sensor. Consider the triangle highlighted in yellow. We know that cos theta is equal to zxl divided by the force of gravity, so we could say that theta is the arc cos of zxl divided by the force of gravity. I believe this is the tilt measurement we were meant to find in Lesson 41. Unfortunately, zxl has the same value whether the sensor is pitched up or down, so the arc cos formula alone cannot distinguish between pitch up or pitch down. Notice that the yxl vector changes sign when the IMU is pitched up or down. We can incorporate yxl into our calculations by using the tangent function instead of the cosine function as shown here. Our theta calculation becomes theta equals arctan YXL divided by ZXL. In a similar way, we could calculate phi as phi being the arctan of XXL divided by ZXL. One weakness of this approach is that it assumes that the IMU is stationary and flat in the X dimension when we're pitching or in the Y dimension when we're rolling. But how do we cope if the sensor does roll when we're pitching or does pitch when we're rolling? It helped me to visualize this by thinking of the existing XYZ axes as world axes and adding device axes on the board shown as X prime, Y prime, and Z prime. The world axes never move, whereas the device axes move with the IMU. Here we see a close-up view of the device axes relative to the world axes. The IMU is flat in the x-axis, so XXL is 0. The y prime axis is pitched up by theta degrees relative to the y world axis, so only a portion of the force of gravity hits the z-axis sensor at 90 degrees, while the remainder hits the y-axis sensor. We can see that all the forces are constrained to the YZ plane highlighted below. In addition to pitching the IMU, if we roll it by phi degrees now, the x-axis sensor will come into play. In the diagram below, the IMU is both pitched and rolled, so some portion of the vertical force of gravity will strike each of the x, y, and z-axis sensors as shown in the diagram. The light gray box in the diagram represents the space in which the x, y, and z forces act. The dimensions of the box are XXL, YXL, and ZXL. So, how do we turn all this trig into a measurement of theta or phi? Consider the triangle highlighted in green, which contains our pitch angle, theta, the right angle between the full force of gravity and the horizon, and an unknown angle we'll call alpha. I've stripped the diagram down to its bare bones for better visibility. The angle identified with the question mark below is a vertical angle. That's vertical in the sense of vertex, not in the sense of horizontal and vertical. An angle on one side of a vertex is equal to the angle on the other side of the vertex. So the question mark is actually alpha. The x and z axes are perpendicular to each other, so the triangle highlighted below is a right angle triangle. The triangle is bounded by XXL, ZXL, and the hypotenuse, which we'll call SXZ. Being the hypotenuse, SXZ is equal to the square root of XXL squared plus ZXL squared. Now consider the next highlighted triangle. It is also a right angle triangle. It is bounded by SXZ, YXL, and the force of gravity. The triangle contains a right angle, the angle alpha, and an unknown angle indicated by the question mark. So we can say that alpha plus 90 degrees plus the question mark equals 180 degrees. Earlier we showed that alpha plus 90 degrees plus theta was 180 degrees, so we can say that the unknown angle is theta. Now that we know theta, we can write an equation for tan theta that uses XXL, YXL, and ZXL as shown here. And equally, we can write an equation for theta that uses the arctan of XXL, YXL, and ZXL, also shown here. In a similar way, using the equations shown, we can come up with an equation for phi in terms of XXL, YXL, and ZXL. So far, our equations for theta and phi are as shown here. The Lesson 42 homework doesn't require the IMU to be pitched or rolled beyond plus or minus 90 degrees, let alone to be upside down. Even so, the atan2 function looks interesting. The atan2 function is an alternative to atan, which considers the sign of both arguments and returns results that are in the proper quadrant. This allows us to report pitch and roll up to plus or minus 180 degrees. So we'll use the arctan2 equations shown here in our code. We all remember the square root of a number can be positive or negative. It seems like the MicroPython square root function always returns a positive result. So the sign of theta will depend on the sign of yxl. We can observe that yxl is positive as you pitch up until you pitch up past 180 degrees. Yxl is negative as you pitch down until you pitch down past 180 degrees. The sign of phi will depend on the sign of xxl. We can observe that xxl is positive as you roll left until you roll past 180. XXL is negative as you roll right until you roll past 180 degrees. We can also observe that ZXL is positive when the IMU is right side up and negative when the IMU is upside down. If we can manage to pitch the IMU without rolling it, XXL will be 0 and our equation for theta reduces to an equation more like the one Paul was steering us towards, shown here. Similarly, if we can roll the IMU without pitching it, the equation for phi reduces to another equation similar to what Paul was steering us towards. There's one last thing to consider before we look at the code. I found the MPU 6050 to be somewhat sensitive to vibration. Paul taught the method of cleaning such noisy data with a low-pass filter in his video 9-Axis IMU Lesson 7, Understanding Low-Pass Filters. Admittedly, this video is about different hardware, but Paul's explanation about low-pass filters still applies. There's a link in the description. Below you can see a plot of MPU.xl.x in blue and a filtered version of XXL in red as I shook the MPU 6050. I used filtered data in my Pico W code. So after all this work, the question remains, are the complicated forms of the equations better than the simple forms? The following Pico W program will calculate theta and phi using both sets of equations. We'll see if the simple equations are more error-prone when we roll while pitching or pitch during a roll. Whether you can live with the error or not will depend on your application. Let's have a look at the code. As usual, we start with some imports. We import MPU 6050 because we're going to be using the IMU. We import I2C and pin so we can use the I2C interface. I'm using the OLED display, so I import SSD1306_I2C. We import math because we're going to be using some math functions, and we import time so we can use the sleep function. Here we configure the OLED display. These statements are where we configure the IMU. And here's where we display the program heading on the OLED. And finally, here's where we define the parameters for our low-pass filter. In a while true loop, we pass each MPU.xl parameter through the low-pass filter to remove high-frequency noise. This creates an X-filtered, Y-filtered, and Z-filtered variable. We limit those variables to plus or minus 1. Here we calculate pitch and roll using the simpler form of the formulas. Notice we're using the arctan2 function to avoid unwanted sign changes at plus or minus 90 degrees. Here we calculate SXZ and the pitch using the more complicated formula. The copy sign function allows the calculation of pitch to extend to plus or minus 180 degrees. Here we calculate SYZ and roll using the more complicated formula. And here's where we clear the OLED display and display our results. Finally, we print the two versions of theta, followed by the difference between them, and the two versions of phi, followed by the difference between them. We sleep for 1/10 of a second and do the loop again. Let's see how it works. Okay, so here's the moment of truth. I have a Draftsman's triangle, so I've got a definite 60-degree, 30-degree slope here. It turns out my desk is not horizontal, so I need a shim to make sure that these angles are right. Here's my breadboard with my sensor on it, the OLED and the Pico. On the back, there's anti-skid rubber to keep the thing from sliding around on my desk. I cut a notch along the long axis and another notch along the narrow axis of the breadboard, so that when I put the breadboard on the triangle, it doesn't yaw. So what we'll do is we'll adjust this so the roll, and I'm going to do it in such a way to get my hands out of the way. We'll adjust this in such a way that the roll is as close to 0 as possible, and kind of like that. And you can see that the simple theta and complex theta formulas both agree. In fact, the difference is 0. Theta diff is 0. Well, that's great. As I start to rolling to the right, you'll see the simple theta starting to climb. The complex theta is climbing, but not as much. There's a 5-degree difference between them. The further I roll, the bigger the difference. Simple theta is up at 42 degrees and complex theta is still at 31. The same thing happens if I go the other way. You can see simple theta now, I don't know, 25 or 30 degrees rolled to the left. Simple theta is up at 37 degrees and complex theta is still at 29. Okay, if we're going to look at the simple phi and complex phi equations now, I need to get the pitch as close to 0 as I can by hand. We can see simple phi and complex phi agree around 28 degrees. If I pitch this down, you can see the difference starting to increase. Complex phi is hanging around the 30-degree mark, and simple phi has already climbed to 37. So in both cases, I think the complex version of the formulas are more accurate than the simple versions, but the simple versions are probably good enough for many applications. That's about as far as I can go with this lesson. Any further, and I might need to learn about Euler angles or quaternions. I'm happy to wait for Paul to explain those. The simple equations work best when we're trying to measure pitch without rolling or roll without pitching. The complex equations work best when we're going to be pitching and rolling at the same time. And the low pass filter seems to improve our accuracy when the sensor is not stationary. In our example, we minimize the effect of vibration, but the same technique could also minimize vehicular or other high-frequency motions as well. Any and all comments are welcome. Don't forget to like or dislike the video before you go. And feel free to subscribe. Don't forget the notification bell. We'll talk to you next time.